You guys are looking at the right thing, right? Okay.
Yes.
Okay.
Yeah.
Okay. Well, I hope you guys are doing well. This is chapter 12 with custom models and training with TensorFlow. So first, if we take a little look at this is like what this chapter is mainly about. So a little bit of a look ahead at what we're going to be doing today. We'll first be looking at TensorFlow and how we can do some operations with it. We're going to compare it to NumPy. We're going to do some type conversions, variables, and we'll deal with some tensor. And we'll also later be customizing models. We're going to be doing custom loss functions, activation functions, metrics layers, models. And very briefly at the end, I will talk a little bit about TensorFlow functions and graphs and their autograph and tracing and some of the rules that you have to do for you to use those TensorFlow functions and graphs. So what are the benefits of dealing with these custom functions? If we look at this slide a little bit, everything that we're going to be doing, like in Keras is a lot of higher level API. So lower level API is kind of like the nuts and bolts of the higher level stuff. So they're going to provide code in Keras for things like means for error or mean absolute difference. But later we're going to be making our own custom loss functions, and we're going to be doing Huber loss. And so these nuts and bolts will help us learn a lot more and give us a lot more control about what our model is actually doing when calculating loss. And having this type of control over our model allows us a great amount of ability to analyze and interpret our inputted data. So this is a quick tour of TensorFlow. So it's similar to NumPy, but it can run computations you support. It can support distributed computing across multiple servers and devices, and it can efficiently optimize its own computations. And so this is what the thing I was showing very briefly earlier. And so TensorFlow itself actually utilizes lower level C++. Each operation is done there, and many of these operations have different implementations, which are called kernels. And each kernel is dedicated to a specific device like CPU or GPU or a T, where that operation is handled best. So flow revolves around tensors. Distributed computing is important to that. And it also includes a compiler natively that allows it to optimize computations for speed and memory usage. So why do we use tensors over arrays? It's like, why don't we just use NumPy for everything? If we think of a picture as an example, and this kind of represents a tensor, if we have thousands of images, that can be represented by thousands of dimensions. So maybe we have like a picture by the width, by the length, by height, depth, by color, etc. That becomes quickly more than an array can handle. So you can make 2D arrays or 3D arrays, but eventually, if you have thousands of dimensions, a tensor is much more efficient for running that computation. So a little bit about type conversions. Every tensor has a type, just like an array. An array can be numbers, or it can be filled with strings or floats. So type conversions are like changing an integer to a string, just like you would in like normal Python or coding. So maybe you can change from a 32-bit float to a 64-bit float. So this is a little bit like a graphical representation of bits. So the first bit is always a positive or a negative. So it'll tell you if it's negative or positive number, and then filled by some numbers. And so this would just be a 16-bit, and this as a whole would be 64 bits. So you can see the difference in the size of how you're representing a number. So type conversions will always, like you can see here, hurt your performance. If you're trying to convert, for example, from 32-bit to a 64-bit, TensorFlow will have to do more computations for you to be able to do that conversion. So if you're creating a TensorFlow like you do here, you use tf.constant, and I filled it with numbers 1, 2, 3, 4, 5, 6. It will automatically, by default, put it into a 32-bit float. So this is like you have kind of like 32 significant figures. Like this is like describing the precision of your number. So this is how you create the tensor. And then you can see here, the way that in which you index a tensor is exactly the same way in which you would index an array. So here we have everything from the first column onwards. So we have 2, 3, 5, 6. And you can also do math with it. And so like here you can add 10. So every number adds 10. And you can also look at the shape, which is 2 by 3. And so here is what I tried to do if you take a 64-bit float tensor and you add it to a tensor that was 32-bit float. So here's float 32, which is T, and T 64-bit is 64. So if you try to do this, it will not let you. It wants you to convert it. So here I did tf.cast, and I cast that 64-bit this here into 32. So now you can do that computation. So some other things about tensors, these are the tensor structures. So there are a couple different types, actually there are many different types, but the ones that the textbook mentions and that I'll go over are sparse tensor. So a sparse tensor is like representing a tensor that mostly has zeros. So if you have a lot of zeros in your data, it's very efficient to run it through this. And a tensor array is a list of tensors with fixed size, but can be made dynamic. And something special about tensors, and something I talked about, I think like 2 book clubs ago, was the difference between tensors and PyTorch. But in tensors, notice that we have to have the same shape and data type, even in tensor array or a ragged array. And a ragged array is a static list of lists of tensors where every tensor has to have the same shape and data type. So you can't just change it. You can't have different size tensors within your list of tensors. And so here, I'll later talk about tensor strings. And so sets and queues I'll show here on this slide. So if we look at a set, I made a set here, which is 1, 2, and 3, 4. So it's like you created a box around 1 and 2, and you created another box around 3 and 4. So that adds another set to it, like a box of 3, 2, and a box of 1, 0. So if you take 3 plus 1, you get 4. You get 2 plus 2, you get 4. So here at the end, I get another tensor set, which is all 4s. So you can do operations between different types of tensor structures. And queues are like maybe you're waiting in line at the grocery store. So a FIFO queue is just like that, first in, first out. So this is a way that you can prioritize the way in which you do your tensor operations. And there are some more structures that we won't go into. But this is a tensor strings, which I think is pretty interesting and very different. We're pretty lucky that a lot of the science world is very English centric. So when I make a tensor of strings like this, I love machine learning, and we have it outputted. It says I love machine learning. But if you notice, I have French here, and you can notice the macron over the E. I think it's called a macron. We'll notice we have something like CAF, XC3, XA9, which is unintelligible. But that's because every time we're putting a string into a tensor, it's not really that language. It's being encoded automatically into UTF-8. So you notice here I have Chinese. So I'll teach you how to say I love machine learning in Chinese, which is 我喜欢机器学习. I like machine learning. And so the way that this is put into it is in UTF-8. So despite the fact that we can have different languages, your tool will be able to handle them all. And so that is pretty important if you're ever dealing with data and text data that's not just in English. So this is about custom loss functions. Here. Yeah, thanks, Shiva. And this is okay about custom loss functions. So there are many times, I'll be honest with you, in lecture where I fall asleep. But I promise you for the next about 15 to 20 minutes, this will be the most important part of the lecture that will understand the rest of it. Like this will be fundamental to everything we do. So I really hope you do follow along with me now. So why do we need to do a custom loss function? What's so important about it? It's because it allows us to create very detailed modifications to what objective we're trying to achieve. And it can help you achieve better results and accuracy. And most importantly, understanding how to build your own custom functions and code will give you a better overall understanding of the higher level API. It's really easy to use Keras and use something like mean squared error without understanding what it's actually doing. So for your loss function, let's just look at what we're going to be doing without even looking at the code. We're going to be dealing with Huber loss, which is sort of like a combination of mean squared error and mean absolute difference. So the difference between these two different types of loss, mean squared error will penalize large errors heavily, and mean absolute difference will not penalize outliers as strongly. So you can see here in this graphical representation, the green line is Huber loss, the blue line is mean squared error. So we're assuming that and this is delta, by the way. So to explain it a little more, delta is like your residual. So if you're, if you just have linear regression, delta is your amount of error. So if we assume delta in this graph is just 1, and let's say I have the number -4 as our error. Actually, no, sorry, I said that wrong. Delta is the limit of residuals. So we're saying it here, like it's combining. Notice that this is the same basically as mean squared error and mean absolute difference, right? It's very similar. So why Huber loss is so great is because if it's a small error, we're just going to use this mean squared error, which is fine, but we don't want to penalize as large as mean squared error does. So if anything is very large, we'll use a different function to solve for that loss. So if you notice here, if we choose our delta as 1 and we say our error is -4, the absolute value of -4 is 4, and 4 is not less than 1. So we use this function. So if this is 1, this is 4, and this is 1/2 times 1, then we get 3.5. So this green is Huber loss. So you notice here, we have -4 as our error, and we get 3.5 as the output. And if we just use normal mean squared error, we would get -4 squared, 16 divided by 2, which is 8. So that's a very high penalty that we don't want to use. And this does exist in Keras, but we're going to pretend it doesn't because we're just going to pretend we're making our own custom code. So now this is how you write the code. And this is how we will write it. So we're going to define it as Huber_fn. This is our function. And notice that it is almost exactly the same as the map. We're gonna have the true value, the predicted value. We're gonna have the error, which is the true minus the predicted. And then we're gonna check, is this error small? So we're gonna pretend here that our delta value here is just 1. So our squared loss is the squared of the error divided by 2. So that's this. And our linear loss is the other function. And all we're going to be doing, right, is delta is 1. And it's 1 here. All we have to do is the absolute value of the error minus 1.5. So the only thing where this might get more complicated is when you do tf.where, which is a TensorFlow function that follows this format, condition, and then x and y, and then name, which means you're going to check the first thing, the condition. So is our error small? Is it smaller than 1? Then we're going to go to the next thing. So squared loss, if it's small, it will do this one. And if it is not small, it will do this function. So that's very similar just to this, pretty much. So I'm going to do it. I did it here already in the code where so I chose the true value as 5 and the predicted value as 3, right? So I'm saying that delta is 1. So the error is 2, and 2 is not less than 1, which means I'm going to do linear loss, which is 2 minus 0.5, which is why I get 1.5 here. And so that's it. That's how we do our custom loss function. And then we're going to continue to use this loss when we compile our Keras model and later when we train it. So there are difficulties that come, however, with trying to write your own custom components. You have to save and also load it in special ways. So it's okay to save your model because Keras will save the name of the function, but to load it, you'll have to provide a dictionary mapping that function name to the actual function. So Cross knows what you're trying to do when you call Huber_fn when you're reloading your custom function. So this is creating your custom thresholds, right? So earlier I was saying that delta was 1, but what if we want to like over here to be something like 2? So notice I didn't even code that, that delta into this, right? This is just absolute error minus 0.5. So here you'll notice I do threshold times the absolute error minus threshold squared divided by 2, which is just this, exactly the same. So going through this code on the right, you can see I've created a function that creates another function. And the reason why we're doing this is, this is the function we've already made, and this is the function that will create the Huber_fn function with the threshold that you choose to determine. And then when you save the model, this is how you have to do it. And the threshold value would not actually be saved. So we have to specify the threshold value when we load the model. And the way to do that is by creating a subclass of the crosses.losses.loss class here. So, let's do some class stuff. So I will show this on code. Okay, can you guys see this?
Yep.
Yeah.
Okay. Remember earlier we were looking at a kind of complex looking code that had to do with classes and class inheritance, and it had to do with something weird that looked like this, which was quargs. Looks very strange, right? But here I'm going to explain it all. So let's say we have a class coder, and I'm going to this looks pretty much very similar to what we did earlier with Huber_fn. So we're going to create our function, and here when we do init, all we're really doing is we're saying we're going to initialize these arguments. And self is just a way in Python that points to those attributes. Sounds kind of weird, but I think it will all make sense when I type this out. Okay, so we're going to have our class coder, and we're going to have a bunch of initialized arguments, name, surname, and birth year. So if I choose to make, maybe we'll have Bob be our coder. And so Bob, his name is Bob. Surname, let's say Bobbert, and he is born in 1980. Right, so a class is just really like a way for you to kind of deal with information, and it will also bridge how you're able to process that information. So if I do something like bob.birthyear, it will give me 1980. And likewise, if I do bob.surname, it will also tell me his last name, Bobbert. Now, let's say, you know how sometimes people will say their birth year and they're like, don't do the math, haha, I'm really old or something. So let's create within the class coder a way for us to calculate Bob's age based on his birth year and the current year. So what I'm going to do here is rewrite the coder class, which I can just copy paste. And then I'm going to put a new method in here, how old. So self current year. And this self is just a way for us to really point at our attribute. It's just a way for us to kind of process that information. And so how old, right, will be equal to the current year minus his birth year. And then at the end, we're going to return his age. So I will have to actually restart runtime to make sure this is using this coder class. Okay, so if I do something like Bob.how old, oh, forgot I have to run this. Okay, and then I'll be able to do something like Bob.how_old. And I put in the current year, right? And it will return 41 to me. And that's because I've given it this current year, but Bob already had these attributes from here. And so what this function is going to do, it's going to take the current year, minus this attribute, so 1980, and we get 41, which is how old he is. And now the thing where everything gets more complicated is we're going to deal with child inheritance. So if we write another class, like let's say product manage coder, what this is saying is product manager is a class that is a subclass of coder. And the way that people in textbooks and Pythons and professors will teach you, coder is a parent class and product manager is a child class. And so what's special about this relationship is a child class can inherit out the coder class, deals and processes those arguments and attributes. So if I do something like this, right, this is going to be exactly the same as how I did earlier, but now I'm going to include the product manager's projects that she's been working on, what company she works at, and then I'm going to have the same thing as Bob, so the name, surname, and birth year. So if we point to the projects, right, and we also point to what company she works for, and then this is the special thing I'm going to do. I'm going to use super. Right, so this is going to be the special thing what we're doing. And what super is doing, it's almost like it's stealing the way in which coder deals with these arguments. So I'm going to run this and then I'll show you and it'll make more sense. So if I do something like Kelly equals product manage, maybe her project so far is cleaning data sets, and she works for Microsoft, and her name is Kelly, and her last name is Lewis, and the year she was born is 1970. Oh, spelled something wrong. Okay. Okay, now that will work. So notice the way in which I've pointed Kelly's name, surname, and birth year. When we were doing Bob earlier, I had to do this, right? I had to do self.name equals name, self.surname equals surname, self.birth year equals birth year. But here I didn't have to do any of that. All I had to do was super and init, and then I pointed to those attributes. So when I'm here, even though I didn't do self.name equals name, I can still get her name just by doing this. And I can also do, to show more proof of child inheritance, is I can also do surname, and it'll give me Lewis, right? So even though I never wrote this code, self.name equals name or self.surname equals surname in this child class product manager, it still worked regardless because of child inheritance. Coder already has the way in which I'm going to process and deal with this data, these arguments here. And so I didn't have to do any of that coding. I just had to do super, and it did it for me. So, okay, that's what child inheritance is. And to further understand the code that we're getting this, we're also going to have to deal with some quargs, which looks very weird, but all it means is it stands for keyword arguments. So first, if we do something like practice concatenating, right? So if we add this together, we can do something like define practice concatenating string 1 and string 2. So what I want to do is I want to add first string to the second string, and then I want to print the result. Then if I write code here that looks like practice concatenate, here I'll do Kelly Lewis. So what this will be doing is it's just going to print Kelly Lewis, right? But then I'm going to try something where I do something like practice concatenate. If I try Kelly Microsoft, if I try to do this, it's going to give me an error, right? It won't work because I only designated there to be 2 strings, but I gave it 3, which won't work. So if I try something like, if I make a new method called like fancy quargs and I just put this in. So notice I'm not putting string 1 or string 2. I'm passing it asterisk asterisk keyword arguments. So then I can do something like result equals for argin. So if I make this new function, we're going to see that it does the same thing as practice concatenate, except that I never gave it like any specified number of arguments that I'm passing through the function. So then I'll do something like print practice. So because it's a keyword argument, I have to like kind of put it in this format. So if I do this, it's going to give me Lewis, right? So this function was exactly the same as practice concatenate, except I never passed it string 1 or string 2. In this method, it does not know how many strings I'm going to attach to it. So remember, I did Kelly Lewis Microsoft, and that didn't work. But if I do it here, I'm just going to copy paste. This will work, right? So Kelly Lewis Microsoft, like so the big differences between the two, practice concatenate and practice quargs, I was able to do 2. I was able to do 3 strings, while this can only handle 2. So I could do 2, 3, 4, 5. I could do 1,000 strings if I wanted to here, and it wouldn't matter because this doesn't care about how many positional arguments you're trying to pass through this function. So I hope that makes sense, because what we're going to be doing is just very similar to that. So I'm going to skip through this.
If this will be the new standard of book club, I'll quit. This is fantastic.
Okay, I'm glad. So, okay, this was the big fancy thing that I was looking at, right? And I was saying, whoa, okay, this is like really complicated. This looks very hard to do. Actually, it's very, very simple. So earlier, what we were doing, right? This is Huber loss is just a child class of Karas's function of Karas's class losses.loss. So remember what we were doing earlier, we initialized some arguments. So here I'm saying the threshold is 1, and then there are a bunch of random keyword arguments. And so I'm pointing the threshold to the threshold, whatever this value is going to be. And then I do super init quargs. So this is going to handle Huber loss. This child class is going to handle everything in the same way that Cross already does. So what we're really doing here is we could code this all ourselves, but we're just going to steal it from Karas because Karas already does it for us. And if we wanted to code it, it'd be very complicated. It would take a long time. So we won't even do any of that. So this is a very simple way to steal the way in which Karas handles loss into our custom class. So I hope that makes sense. So then we're going to do something where we call this. So remember, we have the true value, we have the predicted value, and this is basically exactly the same as what I showed earlier, where we're going to calculate the loss, right? So we're going to check if it's a small error. We're going to do squared error divided by 2. It's basically this function, right? And then we're going to have this get config thing, which sounds a little weird, but it's not too difficult to understand. What we're doing here in get config, we're just returning a dictionary, mapping each hyperparameter name to its value. So it's going to call Karas's get config method, right? Look at the super. I didn't write this thing. Karas is going to handle it basically for me within my own custom class that I made. So remember that hyperparameters are just the adjustable parameters that must be tuned in order to obtain a model with optimal performance, right? So when we're calculating loss, what are we really doing? If we have linear regression, it's like if we have like a linear regression and there's a predicted line, loss is trying as hard as possible to reduce the errors between the predicted and between the true value. So if we're training a model, we need that hyperparameter, that loss, to continually change. And so this is what this is doing. It's going to map that value to what we already have. And this will save the threshold constantly. So we're always going to have the same threshold and it won't lose it. So, okay, so what we've just done, right, is we've written this class, Huber loss, and we stole some attributes from Karas's native loss class so that we didn't have to write any complex code. We could just take it from this. And so it will handle threshold in the same way that Karas does it. And so that way we don't lose our threshold. And then we're going to write our function, and that's going to calculate loss based on Huber. And then this is going to map that threshold so we don't lose anything. So to reiterate what we've done, we've written our last function based on Huber loss. Then we created a function to create another function that allows for us to change the threshold. Remember, it was like in this, right? So we created a function to create another function. Looks like it's here, right? So then we created a subclass of crosses.losses.loss, which already has some really complicated code that we don't have to deal with. And it will handle everything in a way that Karas already does. Remember, so when I wrote product manager in that code on Colab, it was able to handle Kelly's name and surname and her birth year, even though I didn't write it, because it took it from the parent class. So in our child class here, which is Huber loss, I don't have to do anything complicated. I just take it all from Karas. So that is how we wrote our custom loss function. Okay, so everything I've just done will be repeated again for a lot of things. So now we're going to look at custom activation functions, initializers, regularizers, and constraints. But I promise you, if you were paying attention to the last stuff, this is all very simple and very easy, and it will basically be analogous. Everything we're doing here is almost exactly the same, except you might be dealing with more math or different types of functions or things that we're trying to accomplish. So a quick look at what we're going to be doing. We're going to make a custom initializer, which is glorot initializers. We're going to be using custom activation, softbus, regularizers. We're going to be using L1, also called a lasso regression. And then we're going to be dealing with rectified linear unit weight constraint. All of these things might seem kind of complicated, but I will explain them all, and they're not very difficult. And remember, so earlier we made our own Huber loss, and so the code is as simple as this. All we're going to be doing is creating our own custom stuff. This is our soft plus, initializer, regularizer, and our constraint weights. And it's really as easy as this. This is all we're going to be doing. And so this is what it looks like when we then compile our layer and we put everything through it. So a little bit of a background on how our custom loss function compares to our custom L1 regularizer. Remember, so we're going to use this lasso regression, this L1 thing. And so this is the code for that. And this is the code for Huber loss, remember. So the things are exactly the same. We have our child class, which is L1 regularizer, and we have our parent class, Karas.regularizers.regularizers. So the way in which we're going to handle our data is the same way in which Karas already does. We're not even going to code it. It's just going to do it for us when we call super, or just the way that we do this. So what do we do here? We initialize our factor, and I'll explain the math behind lasso regression in a bit. But we have our factor, then we do our actual regression. So this is like the function that we're going to be doing, which will add the absolute value of magnitude of the coefficient as a penalty term to the loss function, also called the taxi cab norm. I'll explain this all. This is like a taxi cab norm here. And so to measure your L1 norm, all you have to do is like a taxi cab, right? A taxi cab may be in New York. It can't just go straight through a building. It has to go around streets, right? So if it's going down the street, then going up the street, it's not as efficient as this. So that L1 norm is just how it had to kind of go through to get to that location, which is 3 + 4 = 7. So as a whole, this is very difficult to understand. These functions always look very crazy. But when we're doing linear regression, right, all we're doing is we're just looking at our predicted line and some actual values, right? So What this is saying is we're going to take our residuals, which is the difference between the actual value and our predicted values. So these are predicted values. This is the actual value. And we're going to square that error. And so we want this to be as close as possible to 0. But the thing we're doing with lasso regression is we're going to be dealing with something called lambda, which you can find on your own. And we're also going to be dealing with the absolute difference, right? So just like this, we're going to be adding it all up. And beta here is it's kind of like your slope. If you think of like y equals mx plus b, beta is your coefficient. This is the slope, this is m. So we want this as a whole to be as close as possible to 0. But the difficulty with dealing with pushing those towards 0 is we might accidentally overfit our training. So as we constrain our coefficient estimates towards 0, there's a problem in our training where, let's see, how do I explain this? Okay, I'll come back to this. I was gonna do some math on my iPad, but I couldn't figure out how to hook it up. Okay, so we're gonna push this towards 0, and the thing is, the lasso will penalize large coefficients, right? So this lambda number is always going to be a small number. So like, let's say 0.05, right? So if our coefficient is something like 5, or our coefficient is something like 700, it won't matter as much for the coefficient if it's 5 as it will for if this coefficient is 700. So I hope that kind of makes sense. It's a little bit difficult to understand. We just want our coefficients to become smaller if it's too large. So that way we don't overfit, like we're not placing too much importance in just one coefficient, because this entire equation will be driven towards 0 because we want our predicted values to be as close as possible to the actual values, but we just don't want to place too much importance in one like instance, which is x of I. Sorry, I think that was a little confusing. But this is basically what we're doing with lasso regression. And so this is going to explain a bit about the Glorot initializers. So a long time ago, back in like the beginning days of machine learning, a lot of researchers had difficulty in initializing the values of their weights. So if we pretend our model is just a simple line like y equals mx plus b, and we pretend that bias, which is b, is 0, then we're trying to create the best possible line matching our function's predictions with the true values, like you can see here. And so they used to start this slope at values of in a boundary of negative 0.01 to positive 0.01. And so it didn't really matter what you're doing because of SGD, you're going to upgrade this. You're going to automatically change these weights anyways. But if a publisher doesn't announce what these weights are, it can be really difficult to replicate those results. And it's also like a very arbitrary system of determining your initialization limits. So these two people, Glorot and Bengio, wrote a paper, I think in 2006, announcing a Glorot initialization method. So what we're going to be doing here is the normal initialization technique, which is just the square root of 2 divided by the number of nodes in plus the number of nodes out. So if you can see here, we're taking the square root, right, of 2 divided by in divided by out. I mean, in plus out. And then we're just going to return that. So this is so we don't have to start at a random boundary. This will determine where we're starting from. And so this is the rectified linear unit and softmax. So when I first heard of ReLU, and I think we talked about this in chapter 4 of the other textbook, it sounds very complicated, but actually it's very simple. If you ever have a weight that's negative, it's just going to push that towards 0. So you can see in this function, is our weight less than 0, then it will, if it's less than 0, then we'll make it 0, right? So we'll never have a negative weight. So this is going to constrain what possible range of weights that we can have. And then with softmax over here, we're going to make our model non-linear. So if you have a bunch of linear functions kind of combined, if you combine a linear on a linear, right, like y equals mx plus b, and you have like y equals tx plus c, and you combine those two functions, you're still going to get a linear function, right? Nothing really changes. So to make that nonlinear, and by doing that, we can create a model with higher power and higher degree of complexity. We have to put it in something like this. So we're going to take our older functions and put it through this. And this is our equation of how we're going to do it, which you can see here. We're taking the natural log of e to the x plus 1. So those are our custom methods that we made, which were just coded by this, right? So this is what we were doing. That's everything. And so finally, we can move past that and also now look at metrics versus loss. So this isn't my math. This was taken from Andrew Ng's Coursera class on machine learning, which is actually really great. I watched from their videos. And so remember that fundamentally metrics are not the same as loss. Remember that gradient descent will continually change loss until it gets to an optimum value. So it must be differentiable. I know I said a lot of words, and I'll post the PowerPoint so you can look back at it. And also loss, remember, is not for us. It's for the machine to update and learn. So it's very likely that loss will not be easily interpretable by humans. If you look at loss and you understand it, good for you, I guess. But you know, if you look at something like a number like accuracy, precision, and you see it's like 99%, you can instantly tell like, oh, this is like a really great model. So metrics is used to evaluate the model, and loss is used for the machine to continue to update it to make the model better, to obtain a better metric. And so you can see here in gradient descent, we're continually taking a bunch of steps down. We want to get to this optimum value, but how do we get there? We're not, the way in which you can save yourself some computational power and effort is by just taking the differential. So that's what we're doing here. That's what it's showing. And luckily, creating our metric is almost exactly the same as how we've created all of our other custom models. So our custom loss function is very similar to our custom metrics function, which I'll show here. Well, I'll show later. But so this is our coding, right? So this is what happens when we compile it. And this is a demonstration of metrics. So we're going to be using precision here. This is like not really machine learning. This is very simple. So precision, remember, is the number of true positives divided by the number of positive predictions. So let's look at this first batch. The left one is the true values, and the second one are the things that our model is predicting. So if you see here, we've made 1, 2, 3, 4, 5 positive predictions. But you can see here that one of them is wrong. The rest of them are right. So we only have 4 out of 5. Our precision here is 80%. And the second thing is our another batch, right? So we have 1, 2, 3, 3 positive predictions. And you'll notice if you match it to this first array, every single one of them is wrong. So we have 0 out of 3. We have 0% precision for the next batch, the second batch. So if we take 80 and 0, our average precision is 40%. But you'll see here in TensorFlow, it actually printed out 0.5. So why do we have 0.5? Because of streaming metric, AKA stateful metric. And this is another one of the difference between metrics and loss. It wasn't taking an average precision. What it was doing, it was adding everything in the first batch to the second batch. So we're actually pretending this is 4, right? So 4 plus 0 divided by 5 plus 3. 4 divided by 8, 50%, which is why we get 50% instead of 40% because of the streaming metric. And you can see here a little bit of the special things about dealing with metrics. In order to obtain the current value of the precision, right? So if you just want to look at like the precision for this batch and not this one, just this one, you can do something, you do precision.result, which will show me 0.8. Then you can do something where you reset everything. So remember, these batches we're going to carry over to the second one. That's why we got 0.4, but I can reset that back to 0. And then I do this again, and you'll notice I get 0.0%. So this is useful if you ever just want to, in the middle of your training or evaluation, you just want to reset the streaming metric back to 0. That's how I did this here. So that's a special thing you can do. Now this is our custom metric class. And notice it's almost exactly the same as the way in which we wrote our custom loss. And in fact, we're actually using the same function. So we're still going to use Huber. Now we're going to use it as a metric. It's not really that great, but this is the example that the textbook wanted us to use. And so you'll notice we're making a child class of the parent class. So how we're going to deal with this Huber metric class, we will use the same way in which Keras already does it for us, which is why we use super here. So if we go through this code, we can see we initialize our arguments. Then we use super to deal with our keyword arguments in the same way that Keras would do it. Then we have our threshold, and we have total, and we have this count right here, right? So what we're doing here, we want to add weight to create the variables needed to keep track of the metric state over multiple batches. Remember, so earlier when we were doing this precision, we had number of true positives divided by number of positive predictions. But here, instead, we're going to be doing something different, where we just do that Huber loss function's value, the total value, divided by the number of times in which we had to run that Huber loss function, the Huber metric function, sorry. So we're going to do, like the total value divided by the number of times we did it. So if we run this metric like 10 times, and we get a total value in the metric of like 5, so 5 divided by 10 would just be 2. So that would be the overall thing. And so here is the Huber function itself, which we've already gone over, right? So this is pretty self-explanatory. Then we have this update state here, which is a little bit different than how we wrote our Huber loss subclass. And this is written so that when we have update states, we're going to update the variables results, which will calculate the final result, which is mean Huber metric over all instances. Then we get that out returned to us, right? So if we have a total value of 5, divided by the number of times you run it, which may be 10, then we get 50. We get 50%. And so remember, this get config is just similar exactly to how we've already done before. We're just going to map this threshold to the threshold, which will help us keep that threshold throughout the entire model. Great. So now we're going to move past that, and we're going to do custom layers. And custom layers is, again, very similar. Everything we've done is going to be similar. Everything's almost exactly the same. So why would you want to create a custom layer? Maybe we're dealing with something that's really exotic that TensorFlow can't provide us with. Or maybe in this example, we're just going to have a repetitive architecture, right? So if the layer goes ABC, 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 we can just set ABC to equal D. So in the end, we just have a bunch of layers that look like D, 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 right? So some things to note, though, by the way, if your layer has no weights, so like rectified linear unit or a flatten, remember, rectified linear unit is just going to push everything that's negative to 0. So it doesn't actually have any weights by itself. You want to wrap that with something called lambda. And this lambda function will just automatically make it so that your it will apply everything in this layer to the inputs. So it doesn't have any weights natively, but it's going to take the input and then put this to an exponential function, and then that will be the output. So that's the whole layer. Even though it has no weights, it's just going to take what's before and then bring it to what's after. So now let's see what happens if we write a layer with weights. So we can't just do that lambda function. So here, remember, we initialize our arguments again, and we also use kwargs. And remember, here's our child class, here's our parent class, and we're going to steal the way in which we do that with super. So we're going to deal with this in the way that Keras layer would already do it. We're just not going to write the code for it. We can just steal it from them. And so we will convert the activation argument to the appropriate activation function using this. And this is just the way you have to deal with activation. And so to build this build method will create the layer's variables by calling add weight for each weight. And the build method is called the first time the layer is used. And by then, Keras will know the shape of the layer's inputs, and it will pass it to the build at the end, right? So how do we know the input shape? It's because we already saw it at the beginning. And so this is how the layer knows the number of neurons in the previous layer to create a connection weights matrix. So basically, we're connecting the last layer to the next corresponding one of the size of the last input's dimensions. So if you have a bunch of Lego bricks, right? If you have a Lego brick And then you have another Lego brick. They have to be the same size to fit on top of each other, right? So, you know, you can't mix and match different brands, right? You can't use Lego and like, I don't know, another Lego company. You can't build back from those same weights. So this is why we have that for that connection weights matrix. And so then the call method will perform our operations, which is matrix multiplication, as you can see here by this @ symbol. We're going to take the previous, and then we're going to do matrix multiplication with the kernel, and then we add the bias. And then we apply this activation function to the result. And that way we output of this layer. So kind of like doing y equals mx plus b and passing it through the activation function to get output from this layer. Then we have the output shape, which returns the shape of the layer's outputs. And finally, the get config method is exactly the same as we've done everything before. And we have to do something special with here, cross activations.serialize, and save the activation function's full configuration. So I know I said a lot of words, and that was probably hard to understand, but if you break this down, it's very simple, and everything is very similar to the way in which we earlier wrote product manager of the class coder, right? So, and here is a little picture that I hope might help you understand a little bit of what we're doing. So if we have our layer here, we have another layer here, right? We need the connection weights matrix. We need to make sure we know the size so that we can do matrix multiplication properly. We need to add our bias, that we need to deal with everything here. And then there's going to be another activation here. And we need to make sure that it has all the right shapes and dimensions and it's doing everything properly. And it's also adding bias properly to the input and then putting that to the output. So I hope that made sense. And so if you want to create a layer with multiple inputs, things get a little weirder. You have to have a call method to be a tuple containing all of the inputs. And then you must have another method like compute output shape. So you can see here, I have 2 inputs, and then I have 3 outputs here. So this is how we get something with the layer with multiple inputs. And so, okay, now we're going to be doing custom models. And I'll tell you a little fun fact about models later, but I hope you've been following around with me. Everything, again, is like very similar. We're going to initialize everything, and we're going to deal with this the way that the parent class does it. So layers, right? The cross parent class here already has a way in which we're going to process these attributes. So we don't have to write it for our subclass that's custom, which is residual block. So we're going to build a custom model that looks like this, where we first go through the dense layer, and we go through the residual block. And this residual block is a dense and a dense, and then it's going to do an addition operation at the end, and it's going to repeat this 3 times. And then before going through the last output dense layer, it's going to go through another one of these. And so this doesn't really make any sense. You wouldn't ever actually do this in machine learning. But this is to show you that despite how weird or nonsensical something is, you can still build it. So this layer will be handled by cross, and it will detect the hidden attribute and see that it contains trackable objects layers here, right? So that the variables are added to the next layer's variables. So, you know, okay, see you know. So these are the layers, the hidden layers, and you're going to add, right, the inputs to the next part, which is C. And then we're going to subclass our model, in which is our final code where we subclass residual regressor to cross.models.model. So our layers are created in this constructor, right? So we're not even going to write code to deal with this. We're just going to steal from the parent class's processing method. Then we're going to use this model any way we want to compile, evaluate, and fit. So something that's special about a model and a layer is a model is actually a subclass of layers, in the same way that a square is a rectangle, but a rectangle isn't a square. So a model is technically a layer, but a layer is not technically a model. And that is, so why don't we deal with models in the same way we deal with layers? Like, why don't I just copy that code from earlier? That's because with the model, you can do special functions like fit, evaluate, predict, and compile. And there are a couple of other things. And also, you wouldn't really want to create something like that. Like, why would you use a square if you need to use a rectangle, if that makes sense? So if we go over the code here, we're going to create the residual regressor, which is what we had earlier here. And we're going to have it as a child class of the parent class here, initialize our values. Then we have all these things. So we're going to have the hidden layer, and we have the block 2, and we have the output. So that's exactly like what we see here, right? And then we're going to have the call function, which adds the previous inputs to the output. And then you can see here, you can save those weights and load those weights using load_weights. This is the only function that I'm showing, right? So you have your file path, which is like, I don't know, C, desktop, whatever you want, and overwrite if you want this to be true. And then you can have your save format. So you'll save your model either in HDF5 or in a TensorFlow format based on your preferences. And so then options is just some extra details. So this is how you create your model, your custom model. Then this is how you save your rates. So even if you don't understand, just remember, this is just very similar to what we did earlier with our custom loss function. And so then we're going to be doing now with custom losses and metrics based on model internals. So this is when you want to look at the internal aspects of your model, right? So like, it looks kind of like this. When you run the code, you can see like what's going on basically inside of your model as it's running. So to define a custom loss based on model internals, we will have a custom regression multi-layer perceptron model with a stack of 5 hidden layers and an output layer. So this model has an auxiliary output on top of the upper hidden layer called the reconstruction loss. You can see it kind of here, right? So this is going to help with the model's generalization. Why? Because when we add this loss to the main loss, we are actually having the model retain as much information as possible as it goes through the hidden layers. So reconstruction loss would be, in our case, the mean squared error between the reconstruction and the inputs. So this first init method will initialize some of our arguments, and it will create a dense neural network with 5 hidden layers and 1 dense output layer. This build will create our extra dense layer to reconstruct the inputs, and the call method here processes the inputs through the 5 hidden layers, then passes the result through the reconstruction layer. So notice that we multiply the reconstruction loss by 0.05 here, right? Because we don't want our reconstruction loss to dominate over the main loss. We still want our reconstruction loss to be a part of this for generalization purposes, but we don't want this to be bigger than our actual main loss. So then it will add those two together and it will return the output here. So if you want to create, so this is a different example of a custom metric. So if you want to create, for example, a cross.metrics.mean object and call it in the call method, like you kind of see here, then you pass it to the reconstruction loss, right, which is what we have here. Then you add it to the model with add_metric here, right? Sorry. So that way you can have Keras display the mean loss over each epoch, which will look like this, right? So this is our main loss, and this is the reconstruction loss. And remember, reconstruction loss should always be smaller because we multiplied it by 0.05. And so this way, we can always retain some information from the previous layers. And that way we can help our model be more general. So it can solve maybe a greater number of problems and deal with more types of data. And so, okay, we're coming to the end of the lecture or the presentation. And so we can compute gradients using autodiff. So why is this important? Why does this really matter? Remember, we can calculate our partial derivatives by hand, as I do here. I actually wrote it out. When we're writing a machine learning program, we will often be dealing with tens of thousands of parameters, maybe more. So the way I did a partial derivative here, but it was a very simple equation. But if we have like thousands of variables, this becomes very easily impossible to do by hand. So let's visualize what this code is doing here in terms of the math that I wrote, right? So we're going to have a function here that takes two variables, W1 and W2. And this function is the same as this, right? So even though this code might look kind of fancy, it's just partial derivatives. Even if you haven't taken calculus, it's not too difficult. So if we take the derivative with respect to W1 here, you take 2 times 3, you get 6 times W1, and you add 2 times W2. When we're dealing with this as our in respects to in the partial derivative, we just treat this as a constant. So this is like 2, say W2 is number 5, right? So 2 times 5 times W1. You take the derivative of that, you just get 2 times 5, which would be here, right? So you get number times the constant. You take the partial derivative in regards to W2, you do the same thing. And so you get 2 times W1, right? Because if this is a constant and there's no W2 term here, this just gets like deleted in our partial derivative. And here you treat this as a constant, right? So if you have a constant times the variable, like 10x, you take the derivative with respect to x, and you get 10. So you get the constant here. You get 2 times W1. I hope that made sense. Then we can see what we get if we put that through this. So the partial derivative in regards to W1, we get 6 if we use these numbers 5 and 3. So 6 times 5, right, plus 2 times 3, we get 36. And here in this second partial derivative, we get 2 times 5 equals 10. So this is what this code is doing, right? So I have these numbers 5 and 3, but the way I wrote it is we're also approximating this to handle this a little bit better with computation. So I get 36, right, which is the same as here, like 10, which is also here. So this code, even though it looks kind of complex, is just the same as basic math. So something special that we can do, however, is we can do autodiff with TensorFlow. So I showed you the manual way in which we calculate our partial derivatives, but here we can have TensorFlow actually do it for us, which is very nice, right? And notice before I had these values, these were approximate, right? So there's like 30.00003, and this is 10.0003, right? But here I have the exact numbers. I have 36, I have 10. So TensorFlow actually can do it for us. So first we define the variables, then we use a special TensorFlow function called gradient tape, and that automatically records every operation that involves a variable. And then we can use this so-called tape to compute the gradients of the result z with regard to their respective variables. Then we get the perfect answers. So this code is basically the same as it, and this code is basically the same as this math. So it's not too hard to understand. Sometimes if you just work it through and just write it out and actually see what type of math they're doing. So some nuance about autodiff, right? So autodiff is great. It calculates our gradients and our partial derivatives for us. And so some things have to be special though about the way in which you do it. So here I have our same autodiff function, right? But so when I go to print the first partial derivative, I get 36, and then I try it again, and I get a runtime error. So why do I get this runtime error? Because this tape is not persistent, and it will delete each time to free resources. So if I run this the first time, it's going to give me 36, which is great. That's the true value. But then I run it again, it's already deleted those values to free resources. So this will not exist. There's nothing here. So to fix this, you have to write code like this here, where you have to set the tape to be forced to watch the tensors and record every operation we try to achieve with them. So here we can get both partial derivatives. You can see here 36 and 10. And this is useful because if you want regularization loss that penalizes activations that vary a lot when the inputs vary a little, then the loss will be based on a gradient of these activations with regards to the inputs. So because the inputs are not variables, we need tape to watch it for us, which is this code here. So custom training loops for cases where fit is not flexible enough. So fit will only use one optimizer, right? So the textbook brings up one example where they bring up some paper and they mention that the paper has 2 different optimizers. So fit can only handle one. So we have to write a custom training loop to be able to handle 2 optimizers. And you can also choose to write a custom training loop to feel more confident about what your fit is doing. It also helps you learn, right? So by writing your own fit, you can really see what TensorFlow is natively doing. And you should note, however, though, that writing your own fit method makes you vulnerable to longer code, right? So I'll show you here. It looks very messy. And it's harder to maintain. So you should really only use a fit in concept, but never in practice. So you really shouldn't try to write this yourself unless you have to, or you're just doing it to kind of like see and practice what's going on. So if we build our simple model here in this first block of code, then we want to create a small function that will randomly sample a bunch of instances from the training set in random batch. This function here. Then we want to define a function that will display the training status, as we can see in print underscore status underscore bar. So all this is pretty self-explanatory. None of it is too bad. If you look at it long enough, you would kind of get it. So let's see what this is kind of doing. So now when we run and do stuff, we have our, we have to define our hyperparameters and choose the optimizer, the loss function, and the metrics. So here we'll just do some simple things like mean squared error and mean loss here, and mean absolute error for metrics. So we're not dealing with custom stuff anymore. We're just dealing with stuff that Cross comes with. So then we write out our custom loop. Look very odd, but I promise you it isn't too bad. So what we're doing here, we're creating 2 nested loops, one for each epoch here, and then the other for batches within the epoch. So then we sample a random batch from the training set, and inside the tf.gradient here block, we make a prediction for one batch and compute loss, which is main loss plus the other loss. So you can see it here. And then since we have a mean squared error function that only returns 1 loss per instance, and then we compute the mean over the batch using tf.reduce underscore mean parentheses. Then the regularization losses are reduced to a singular scalar each. So then we sum them in tf.add underscore n here. And then we have to tape, remember, so we did this earlier to make sure we can calculate our gradients with autodiff and apply the optimizer to perform a gradient descent step. So this is like trying to find the best optimum coefficients for our model. And so then we want to update the mean loss and metrics, and we display the print status bar. So that was pretty complicated, but I promise you it's not too bad if you break everything down into their own like little sections. So like, you know, you could break down this gradient tape as a thing that we did earlier. And remember, we're just looking at batches from within each epoch. So this gets very complicated, you can see, right? So this is why you don't really want to write your own fit function, and why you often want to, as if it permits, you want to just use the native one that TensorFlow and Cross already comes with. So then you have TensorFlow functions and graphs. So we're on the last topic. Thanks for listening. And so we have our cube, right? So if I take cube 2, what do I get? I get 2 to the 3rd power, which is 8. And then if I can also do the same thing, however, with a TensorFlow, right? So if I take this function, which is just written, right, for Python, doesn't have to do anything with TensorFlow, I can still pass 2 in and I still get 8 out. But you can also make it into a TensorFlow operation. So you can, like this, right? So we make this cube into a TensorFlow function. And so TF cube, you can see that's made into a function, and we pass 2 into it, and we get 8. And then you can also use a TensorFlow function to pass through a TensorFlow, or a tensor, sorry. Then you get 8. And you can also use a decorator like this to do that in another way. So why is this really important for you to have these TensorFlow functions? It makes your operations faster. It upgrades them. It makes it more efficient for you to get the same output, right? So I still got 8. This was 8, but I did it more efficiently. So some rules that you want to make sure you know. Make sure you're using TensorFlow constructs, like tensors and variables, like here, right? And make sure you're not using like a NumPy array, because then you wouldn't be able to upgrade it into the TensorFlow function. Okay, and that was the end. And so these are some things that I talked about. So like the thing about classes, I really learned from here and here to teach that. And then there was like the loss functions, Global initialization, if you want to learn some more about them. And activation functions are here. And this is Andrew Ng's Coursera course, which I can't recommend enough. It was really great to learn from him. And this is very good to help understand machine learning. Okay, thank you.
Yeah, that was really good. That was really
Wow.
Thank you. Thank you.
That was really good, man. That was very, 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 very
Thank you.
good. Yeah. I mean,
It's gonna be a really tough act to follow.
What? If Toby was here, I would say we've been blessed. I mean, this was very, very good. This is like a landmark lecture, you know.
Thank you. Thank you.
Yeah, you made it very easy. I mean, also there's a very, very big improvement from the first presentation. This is
Yeah.
yeah,
It's true.
yeah, awesome. Zach and Chima, do you have any comments, questions?
I mean, I think I like 3 things. Like, oh, I like the whole thing, but in particular, I like 3 things. One, like I didn't know that the TensorFlow that supported the languages all in the same way. I thought that was really cool. That it stores everything in the same way. I also really liked how you started talking about like class inheritance with a really basic example of the coder and the product manager, because I think if you just jumped right into, you know, saying, oh, like you just inherit, you know, from Keras all the different functions, it would have been really hard to follow. But when you gave that really basic example and then like built on it, it I think made everything make a lot of sense. And also just going more in depth, like I never really thought about using 2 optimizers or 2 loss functions, which I think could really help a model. So just really appreciated you kind of pulling all of that information together really nicely.
Yeah, thank you. When I was going through the textbook, I had to Google a lot of stuff, but I realized that like I would look at like blocks of code, and I would just be kind of I don't know, sad. Like I would look at it and I'd be like confused. I'd be like, oh my gosh, this is so difficult. But I thought the coder thing with the product manager, I tried to show that a lot of the things that we're doing are actually just very simple. Like they're not very hard at all. And like when I looked at the math for some of the things that we're doing, they weren't too bad at all. So I don't know. I hope that's what you guys got from it.
Yeah, definitely. I got that vibe too.
Yeah. No, I mean, this was a very, very hard topic, and you just crushed it. This is just amazing. I'm very, very proud
Thank you.
and just happy about this, you know. And so I'll actually stop recording. And